Welcome to this recording about decision trees. Before we do this, what I want to go into, like as I do sometimes, I want to repeat some essentials of mathematics that you need in order to understand the different approaches. And sometimes we even have encountered these approaches already partially. And for example, in our last recording, we already looked at entropy and cross entropy. Now let me briefly rehash what both is for. And I assume actually that you have encountered this at other occasions, so it's really more rehash than anything else. So entropy was invented by Shannon as a measure of information content or as a measure of uncertainty, both actually, because the question that Shannon asked was like, how much information is conveyed when I send a certain signal, let's say over an airwave or over some cable. And this is described by probability theory, namely given a random variable x, we can describe the entropy eta of x, eta being the Greek letter eta, as defined of minus the sum over all the possible value assignments that the random variable x can take. And for each value assignment, we take the probability of that value assignment times the logarithm of the very same probability of the value assignment. So basically, I weigh each, each information content is described as the logarithm of the probability of its appearance. So it's something that appears infrequently has more information content than something that appears very frequently. But then its contribution is only relative to its frequency, its relative frequency. And we have here a logarithm. We can choose any basis. Very often the basis 2 is chosen for the logarithm. So we have the logarithm dualis. And there are equivalent formulations of the very same formula. We can describe the entropy of x as the expected value of the information content of x, or the expected value of minus the logarithm of the probability of x. So here, of course, the expected value goes through all the possible value assignments with their corresponding probabilities. So implicitly, this part here is hidden in the expected value. This is very easy to understand when we look at the entropy of a fair coin toss. So let's look at a random variable. We have a coin and we throw it. So we either have head or tail as the two possible value assignments we can have. And the probability for x taking on the head is the same as the probability for x taking on tail. Both is 0.5. And now the question is, how uncertain am I about the coin toss? Or when I learn about the coin toss, how much information do I receive? This is really about the same thing. So according to the definition of entropy, this means I have the probability of 0.5 for head times this information content of learning about head, plus 0.5 for tail times the information content that I receive information about tail. And we have a negative sign in front of that. And now if I compute this, the logarithm dualis of 0.5 is minus 1. So this is 0.5 times minus 1 plus 0.5 times minus 1, which is minus 1 times this minus is exactly 1. And this is one bit of information. So when I choose between head and tail, or between 0 and 1 with a 50% chance, and I learn about this event, then I have received one bit of information, which is very intuitive, right? So exactly one bit of information that I learned. Now, if I have an unfair coin toss, so let's assume the probability for head is 0 and the probability for tail is 1, then this formula changes. Namely, then I have a probability of 0 for head, which is 0 times anything is 0. Plus I have a probability for tail is 1 times the logarithm for 1, but the logarithm of 1 is 0. So I have 0 plus 0 is 0. So when a coin is unfair, it always gives me tail. There is no surprise, there's no uncertainty, and there is no information content that's conveyed when I learn that the result of this coin toss was actually tail. Therefore, the entropy is 0. Now, instead of entropy, we can also define cross entropy. So for discrete probability distributions, P and Q, so they may, for example, have different probabilities on the coin toss. I can look at, but it's important here that these probability distributions work on the same probability space, on the same possible value assignments. Then the cross entropy is defined as eta between P and Q, which is the expected value over the probability distribution of P of the information content of Q. So I look at how probable is it that P has a certain value assignment times the logarithm of the value assignment of the second distribution, and I go over all the possible values. And this describes to some extent how far Q is away from P. Let's take one specific case. Let's assume that P and Q are the same distributions. Then this formula would be the same as the entropy itself. Now, this of course is not always intuitive. When I want to answer the question, how far is Q away from P? And I ask the question, how far away is P from itself? Then that's the same as the entropy of P. And the entropy of P is, if I have a reasonable distribution, usually not 0. So indeed, what I get is that the cross entropy between P and Q is always the entropy of P plus the Kalbeck-Leibler divergence between P and Q as defined on the next slide. So the Kalbeck-Leibler divergence, also called relative entropy, is defined somewhat differently. It's defined as the probability of having the value assignment of x times the logarithm of the fraction between P of x and Q of x. And this is then more naturally a difference between these two distributions. And it can also be generalized, actually, like also the other formulas for entropy and cross entropy can be generalized to continuous distributions by summing over infinitely small values x. So relative entropy or Kalbeck-Leibler divergence answers better the question, how far is the distribution Q from the distribution P? This is often something that we ask in machine learning because we want to have a model that gives us the correct assignment according to an empirical distribution. And so the relative entropy measures the expected number of extra bits required to encode samples from P using a code optimized for Q. There is one drawback. The distance is not symmetric, but at least the Kalbeck-Leibler divergence between P and itself is 0. So you can easily check this. If you have here instead of Q of x, P of x, then you have P of x divided by P of x, which is 1, and the logarithm of 1 is 0. So the Kalbeck-Leibler divergence for between P and P is 0. Now, what we typically want to do is, as I said already, we have some empirical distribution in form of our training data described by xi's, yi's. And now we want to have a model that correctly predicts this training data, which means that our predictions should report the same distribution as our training data reports. And that, of course, means that we want to maximize the likelihood for our model over parameter configurations beta. Now, the parameter configurations, for example, in a multinomial means how probable is it that I see a particular value. So this is this conditional probability given a certain object. What is the classes? We had this before, right? Now, when I predict in a given training data set a certain class a certain number of times, then I can, for each particular class, select a particular QJ, and for any class, I just count how often this class arises. And so this gives me an overall product for each class, a different probability, and to the power of how often this class arises, and I multiply this for all the different classes, and not any longer for all the different data points. So when I do this, I can optimize this likelihood by optimizing this term where I counted the class occurrences. And instead of optimizing this likelihood, I can optimize the log likelihood. I can also divide it by n. This is just a constant factor. And when I take the logarithm of this likelihood, that's the same as the sum over the logarithm of Qj. Now, this numbers of how often a class appears, this can be brought in front of the logarithm, because otherwise it would be up here. And the n can be introduced as into the denominator here. Now here I basically count how often does a class occur relative to all observations. So this is nothing else than the prior probability of the class as empirically observed. And this is a certain distribution over classes. And here I have the probability for each of the different classes. And this is what my model gives me. This is what's in the training data. This is my model. And now this is the formula for cross entropy, or the negative cross entropy to be more precise. I look at the negative cross entropy between the observed distribution and my predicted distribution. And when I basically have the same distributions here, this means, of course, that I have a very small difference. The difference, of course, is never, or the cross entropy is never smaller than the entropy of P of y itself. So maximum likelihood optimization is equivalent to minimizing the cross entropy. That's what I say here on this slide. Okay, this was an intermezzo for talking about entropy, cross entropy, and Karlbeck-Leibler divergence. Maybe good if you always remember this, where did I have it? This formula here, that the cross entropy is the entropy of the first component plus the relative entropy between P and Q, between the first and the second component. Good. Now let's talk about another classification method. And just as a side note here, decision trees are used for classification. However, we can modify them also in order to do regression. And that's true for basically any of these approaches. We can either do regression with them or we can do classification with them. Of course, we always need to have some minor modifications. And in the lecture, I typically only show you one approach, but this does not mean that the other approach wouldn't exist. So I could use decision trees for regression. In order to describe how to learn a decision tree, what we first want to know as computer scientists, we want to know the structure of a decision tree. So what is the data structure behind a decision tree? And I indicate this here based on an example that looks at the mushroom data set. What does decision tree have? First, it has inner nodes, starting with the root node, but there are also other inner nodes. Each inner node is labeled with one attribute name, and this is why it's also a univariate decision tree. Univariate meaning we decide based on a single attribute how to walk down in this tree. Then from a node, there are outgoing edges. And these outgoing edges are labeled with values from the domain of the attribute in this node. So if I have cap shape, I must take all the possible values of this attribute cap shape and have them on my outgoing edges. In this case, I only have two outgoing edges, but all the values are assigned to one of these two outgoing edges. So here, X is assigned on the left, and the other three are assigned on the right outgoing edge. And here, what we do, of course, we represent with these outgoing edges how we would decide if a new object comes in. We would look at the cap shape and decide, if it has the attribute X, cap shape equals X, then I would go left. And if it has the cap shape, for example, flat, then I would go right. Then I have child nodes. And the child nodes, for example, here it's habitat and edible, they segment the data. So if an object comes here, I follow according to the attributes to go to one of the child nodes. And when I do this several times, eventually I will arrive at a leaf node. Leaf nodes are those nodes that do not have any further children. And the leaf nodes are labeled with classes. So each leaf node has exactly one class label. And when I initially have an object, I want to classify it, I come from the root node, I look at the attribute, I look up what attribute value does the object have, and then I go along the corresponding value to the next node, and I repeat this iteratively until I end up at some leaf node, and there I read out the class label to know how the object is supposed to be classified. So this decision tree has a structure of inner nodes labeled with attribute names, edges labeled with attribute values that correspond to these attribute names, and in the leaf nodes, I have class labels. That's the structure. So here is the classification process that I talked about already. I get a new object with some attributes, and the object follows the path in the tree until I reach the corresponding class label. Here for this object description, X and D, cap shape was X, so I follow this, I come to habitat, and the D stands for the woods, and I follow that and find out that this object is predicted to be edible. This is the classification process, sometimes called inference process. Now, by this way, by cutting the input space according to such walks from the root to the leaf nodes, what do I do? I basically distinguish incoming objects, and I always do a split. I do a first split, maybe because of the shape of the cap, into some right part and into some left part. And maybe then I look at the habitat and I distinguish, and maybe I have some more attributes that I distinguish and that allow me to describe certain classes more and more precisely, like with 2 or 3 or 4 or more boundaries, each boundary describing between certain values on the left and certain values on the right. The advantage of such a decision tree is that I can look at such a tree and interpret the model quite well, because I know that if this and this and this applies, if the cap is, for example, X, don't remember what X stands for, and if the habitat is woods, then it's edible. This becomes challenging if the tree is very deep or very broad. So now I had a tree where I always had a binary split. That's not necessarily required. I could also have a split into 3 or more children, depending on how I use outgoing edges in order to represent all the possible attribute values. Of course, we go back, we could possibly have another edge, but of course, every particular attribute value may just be assigned to one outgoing edge here, not to several edges. Otherwise, I wouldn't know where to go. Now, the question is, which tree is a good tree? I can construct tons of trees that show similar behavior. And implicitly, what I try to do is I try to optimize a loss function such that I correctly predict my training data most of the time. When decision trees came up, it was typically not called a loss function at that time. And with decision trees, also I have a kind of a greedy algorithm in order to try to come up with a good tree. And the construction of that tree happens in an inductive manner. So I start with the first decision. Based on this first decision, I do a second decision, and so on and so forth, until I hit some stopping criterion. What is the general idea? The general idea is that I grow my tree from the root. So I have a root node, which is unlabeled. Initially, this root has no intention. That means it doesn't have any attributes yet assigned. And the root is assigned all the objects from my training data. Or instead of all training objects, I could also say the total extension. And now I look at this total extension. I look at all these training objects. And the inductive principle is that I check which attribute is best suited in order to split this extension in a way that's most beneficial. So we grow this root node, some children, and what I want to achieve is that the children are more pure in the prediction quality given the training data. So let's say I select a particular attribute, like the attribute I. Then I partition my extension, and according to the different values that this attribute I can take. And this splits this overall set of objects, in this example here, into 3 different sets. Now here I do quite well, because you see the rightmost child has only objects from one particular class. So I have a very pure set here, where before it was a very mixed bag. On the leftmost side, I'm also doing pretty well, because there's only one outlier, all the other ones are blue. And here in the middle, it's a bit mixed. So before I had a very mixed bag of objects from the 2 classes. By selecting a particular attribute I came now with 3 smaller sets that partition this original set, and 2 of them are already rather pure, and the middle one is not quite perfect. Now, I could stop here and just say this child node C always comes with the yellow class. The child node A always comes with the blue class. I'm aware I do a little bit of a mistake. And even for the middle one, I could say it's the yellow class, and I do a bit more mistakes here. But in general, of course, I can also apply the same inductive principle again. For example, I could say this is not a good enough split of the extension assigned to this child node, and I grow my tree from this point onwards further. Now, how do I grow my tree? How do I decide what is a good split and a less good split? And what I use here, and that's why I brought this intermezzo with entropy, is actually a matrix, is entropy and information gain. Again, here we have our formula for entropy. The entropy of a distribution is the probability for value assignment times the logarithm of the probability of this value assignment for all the different value assignments. Now, let's just look at an example. Let's assume I have 4 different classes and the probabilities of these 4 different classes are like this. Then I use this formula and I end up with an entropy of 1.9. You could also say it's about 2 bits of information. And this is because all of these 4 classes have about the same probability. I mean, there's a little bit of variance here. If I look at a different distribution where the second class is much more likely than all the others, I have a very small entropy of this distribution. Because of the spike and the low numbers here, I have almost no surprise. I know that when I know this distribution and I get information, I will most of the time have as a result that the second class applies. And this is a very small amount of information, 0.242 bits, when I use this formula for calculation. And when I have a uniform distribution, actually this is where the most information gets over. If all 4 classes are equally likely, I have 2 bits of information from these 4 classes. So the low entropy means that I have a skewed distribution. The skewed distribution provide better predictions. Yeah? Whereas if I have a high entropy, my prediction is not very good. There's a lot of uncertainty remaining. So here we apply our entropy always on the observed class labels. We ask how certain is a prediction or how much uncertainty is involved in the prediction given a certain extension in a corresponding node. And what we try to do is by splitting a node into child nodes, we try to reduce the entropy in the child nodes such that our predictions get better and better and better. So if I again have the same kind of split I showed you before, then originally I have 10 orange and 8 blue objects. I apply the formula and I have about 1 bit of information, entropy 0.997. I mean, 10 versus 8 is almost the same like 9 versus 9, and 9 versus 9 is like 1 versus 1. So this is about an entropy of approximately 1 bit. Now I do child node A because of using the attribute I, and I have 1 orange and 6 blue objects. So this is an entropy which is about 0.6. Applying the formula, I have child node B. This is more 1-on-1. This is more entropy close to 1 bit. And then I have child node C, and here I have only 5 orange objects. Therefore, I have no uncertainty about what I have to expect in this node, and therefore I have an entropy of 0. Now, here I had an entropy of 1 in the root node. And now when I look at the average or the weighted entropy in my child nodes, this is reduced because here is an entropy of 0, here is an entropy of 0.6, and only here in the middle part, the entropy hasn't changed that much from the original. But when I average or weight that, then the overall result will, of course, lead to a reduced entropy. Knowing where the objects fall will give me information and allow me to better predict which class an object belongs to. So for the children, what I will do, I look in all the children of my current tree. So if T is a node, then children of this node is a set. And I look now for all the children of this node T. I look how probable such a child is. And the probability is, of course, given by the number of objects that I put into this child times the entropy that I observe in this child. So this is the probability of first landing in this node and then the entropy observed in this node. And so what I get here is a weighted average of entropies observed in the children. Now, this is what is in the children. I can, of course, look at the difference between entropy in a node and the expected entropy in its children. This is then the information gain. Initially, I had this uncertainty, namely entropy of a node, and then I subtract the weighted entropy as it occurs in the children, and the difference between the two is the entropy reduction or the information gain that I had by doing the split up according to a particular attribute. So when I go from this set of objects to this split up here, I start with an entropy up here of 0.977. I subtract the weighted entropies, weighted because here I have 7 nodes in child A, 6 nodes in child B, and 5 nodes in child C. So 7, 6, and 5 out of 18 land in these different child nodes, and the first child node has 0.59, the second child node 0.91, and the third child node a 0 entropy. So this weighted entropy at the children gives me a term of about 0.5 something, and the difference to the original entropy gives me an information gain of 0.441. So now I know for a particular attribute I how large the information gain is. Now, which attribute do I want to choose here? Which attribute do I want to label in a particular node? Of course, I'm interested in an attribute that gives me a large information gain because I want to reduce the uncertainty as much as possible. So the decision tree induction then proceeds as follows. I start top down from an empty root node and apply the procedure grow tree to the root node. The grow tree procedure starts with an empty node. Now, there may be a stopping criteria. I check this. Let's talk about this in a slide later. And if the stopping criteria applies, I just say what is now the most frequent class, and that's the kind of label that I will give to this node. But if the stopping criteria does not match yet, then I make this node to become a decision node, and I choose an attribute that maximizes the information gain that allows me to reduce the entropy. I introduce empty child nodes. Now it depends, of course, on what are the possible value assignments for this attribute. And then for all the child nodes, I apply grow tree again, check for stopping criteria, and then possibly further grow the tree. Now, what are stopping criteria? For example, 0 entropy, of course, is a good stopping criterion. But it may also happen that I have too few instances. So if I only have 3 instances left, it doesn't make sense to build a more fine-grained tree, actually earlier than that. Maybe also the attributes don't give me a good possibility anymore to improve my entropy. So let's look at our mushroom example. We have an entropy root node. We have 100 instances, 21 of them being poisonous, 79 being edible. So we have an entropy 0.741. Let's look at the cap shape. And the cap shape has the 4 different value assignments, certain number of poisonous ones over these different values and edible ones, and total ones per particular value. So when I split up according to cap shape, the cap shape B gives me a 0 entropy. That's good, great. The F gives me still some leftover entropy. The S 0, 1, and well, most of them don't reduce the entropy that much. Actually, you could even say this is a large entropy, but only a local one, only applying to 54 of the objects, relatively speaking. So now when I take all that, the expected entropy will be 0.565, and this is smaller than the 0.741. I have an information gain, which is the difference, 0.176. I could look, of course, instead of the cap shape at the cap surface. Again, I have 3 values, and I do the same kind of procedure. I come up with a smaller information gain. I could look at the cap color, and I have a larger information gain, and I could look at habitat, and that gives me actually the largest information gain. So when I know now what the largest information gain is, I construct my tree correspondingly. I label this node habitat. I have outgoing edges for all of the 5 different values. And I end up with certain numbers for how many poisonous and edible mushrooms I have in each of the 5 different child nodes. Now, when I when I apply my grow tree procedure iteratively, I determine that there is no entropy here, no entropy here, no entropy here, so I can label them, and they are all labeled as edible. And that, of course, this means I can compress my tree and merge these nodes, which typically happens by a post-processing procedure. So I have habitat, and 3 values lead to edible, and 2 values lead to inner nodes on which I apply my grow tree procedure iteratively. And yeah, for example, here I have 36 mushrooms in this node, and I still have this entropy in this node. And now I look again at all my different attributes, the ones that I have not used yet. And I look at how they play out. I look at the information gain. I repeat this for the other attributes. And in the end, I decide that, for example, chill size here has the biggest information gain. Chill size leads to 2 children nodes. And this node has 0 entropy, so it can be turned into, or it can be labeled as a decision node. And this has still a very high entropy. So I would now either stop here because I cannot make a good decision, or I would grow this further. But of course, I have to be aware that I only have 16 mushrooms left here. So there's already a small number. And of course, I have then to also look at these other nodes that remain. Okay, so that's how the procedure works to construct this decision tree. And now, what if I had a perfect predictor attribute? An attribute which would be perfectly indicative for the class label. Well, let's assume we have an additional one like odor, and we would have the information that this new attribute would lead to perfect entropy when I distinguish for the value of this odor. That would give me a perfect information gain, and odor would then lead to a very small decision tree. That would be ideal for us. Of course, what we have to do when we construct decision trees this way is we have to look at overfitting. But that's not something that I will do today. Rather, I stop here the recording for this week, and we see each other in 2 weeks from now.